Okay, good morning, everybody. Let's get started. So today we're going to finish up the last part of a fuel utilization, which is we're going to talk about the metabolic disease, diabetes, and then we start to talk about the fuel utilization in exercise, right? So diabetes, we know, have two different types, type 1 and type 2. Type 1 basically is caused by insulin deficiency, right? Means that the beta cell, pancreas beta cell, is not able to produce insulin, so lacks of insulin. And the treatment is pretty simple. Just give the patient, the insulin, right? So insulin supplementation should cure the type 1 diabetes. And type 2 diabetes is much more complicated. The cause of type 2 diabetes basically is the insulin resistance, means that insulin action is reduced. Insulin cannot efficiently does its function. So the insulin level actually increased in the type 2 diabetes. Its body actually compensated to increase insulin levels, try to to compensate insulin deficiency, insulin resistance, right? To make more insulin and to increase insulin actions. Basically for the type 2 diabetes, and we usually encourage them to eat healthy and do more exercise. We know, remember the exercise, one of the benefits of the exercise to stimulate GLUT4, move to the cell surface and of the skeletal muscle cells, right, to uptake more glucose from the circulation, reduce the blood circulation glucose levels. But in the very late stage of type 2 diabetes, they also have insulin deficiency. The insulin levels are also decreased because of beta cell failure. So beta cell cannot make enough insulin. So at this later stage of type 2 diabetic patient, we also need insulin therapy. So now let's talk about the mechanisms. We know that the three important tissues or metabolic tissues that involve in the regulation of glucose homeostasis or metabolism. Do you guys still remember, right? What are the three important tissues that regulate glucose metabolism? Mean the glucose uptake. Liver, adipose tissue, and skeletal muscle, right? So three major metabolic tissues that regulate blood glucose levels. So let's talk about adipose tissue in insulin resistance type 2 diabetes. What is wrong or what happens in the adipose tissue in insulin resistance? First of all, we know that insulin has two main functions in adipose tissue, right, in terms of energy metabolism. One is they regulate glucose metabolism, right? Another important thing is the regulate lipid metabolism. So let's see the insulin regulate the glucose metabolism. We know GLUT4 is the major glucose transporters that respond to insulin in adipose tissue, right? Remember this? And what insulin does to the glucose metabolism is insulin binds its receptor on the cell surface. This represents the cell membrane of adipose cells, right? So insulin binds its receptor and transduces its signaling signals to GLUT4 and stimulate GLUT4 move to the cell surface of the adipose cells, right? And uptaking glucose from circulation into the adipose tissue, adipose cells for metabolism. And this just represents the plasma in circulation, right? That's part. So in the insulin resistance type 2 diabetes, because first of all, group 4 levels is decreased, right? Group 4 expression levels decrease means that in diabetic patients, their adipose tissue have a less group 4 expressed. And secondly, the group 4 translocation from inside of cell to the cell surface, and this process also reduced because this process requires insulin stimulation, right? Insulin action. So if insulin action is reduced or insulin resistance, and this process is also slowed down or decreased, so you have less group 4 being transported into cell surface, right? So then the glucose uptake will also be reduced. Right? Let's see this, in insulin in a type 2 diabetic patient, the insulin signaling is reduced because of insulin resistance, right? So block the group 4 translocation to the cell surface, and then decrease the glucose uptake into the cells. So you have a less glucose inside of cells, right? But more glucose being remain in the circulation, right? So this is one of the important causes of increased blood glucose level in the type 2 diabetic patient, right? It's one of the important mechanisms. And let's see about the other functions of insulin. It regulates lipid metabolism. Remember how insulin regulates the glycolysis. Say that again, sorry. Insulin, in which physiological condition insulin level is high? Fat, right? And in fat condition, do we need a lipolysis? No, right? So that means in the fasting condition, right? So insulin basically is to inhibit lipolysis, right? We don't need fat as an alternative energy. We have enough glucose in the fat condition, so we wanted to inhibit the lipolysis. So insulin basically inhibits lipolysis. So what happened to the insulin resistant cells? If insulin actions decrease, how does this to the lipolysis? HSL. Increase, yes. So HSL levels increase, and which stimulate hydrolysis of triglyceride and break down triglyceride to glycerol and fatty acids, right? So you have increased fatty acids in the diabetic patient, and then fatty acids then be released into the circulation. So that's why in type 2 diabetic patients, they also have high levels of fatty acids in the circulation, right? We talked about this earlier, right? And third thing that insulin does, remember that LPL, lipoprotein lipase, right? It's produced by adipose tissue, and also it's regulated by insulin. So in the insulin resistant cells, the LPS secretion will be reduced, right? The insulin cannot efficiently to stimulate LPS to release, so LPS release is decreased. And what LPS does? What is the function of LPS? LPL. Hydrolyze triglyceride, right, in carmine-1 and VLDL and break down to release glycerol and fatty acids, right? So if this process is being reduced, then what happened to triglyceride level in the circulation? We'll have higher triglyceride levels, right? So in the diabetic patients, again, the blood glucose levels increase and fatty acids level as well increase, as well as the increased triglyceride levels, right? in the type 2 diabetes patient. So this is something that adipose tissue contribute to blood glucose level, fatty acids level, and triglyceride level in the, again, the type 2 diabetic patient. Now let's look at the muscle. The most important function of muscle, do you guys know what is the most important function of muscle in terms of blood glucose level maintenance? Glucose uptake. What is the main function of important function of skeletal muscle in terms of regulation of blood glucose level? Yes. Note, it related to insulin, you know, in the fat condition, for example, in the fat condition, how muscle does to regulate insulin, glucose levels. Right. Thank you. So in the fat condition, we know that insulin levels increase, right? The muscle is a major insulin responsive tissue, right? The insulin stimulate GLUT4, go to the cell surface of skeletal muscle and pick up glucose from circulation, right? So muscle, thinking about the large mass of the muscle in the body. So muscle is the most important tissue that takes up glucose from circulation into the cells and oxidize, right, in the fat condition. So muscle is most important tissue that clean the glucose, right, in the fat condition in response to insulin. So in the insulin resistance, the muscle is really the most important tissue that causing the circulating blood glucose levels increase, right? Because insulin. So in the skeletal muscle, the glucose GLUT4 expression level is not changed. Means that normal people and diabetic patients, they have a similar amount of GLUT4 expression in the skeletal muscle, but the problem is the translocation GLUT4 from intracellular to the cell surface. This process is also reduced because of insulin resistance, right? So insulin, so GLUT4 translocations decrease. You have a less GLUT4 on the surface. The decrease. This will causing the decrease in the glucose uptake, right, by the skeletal muscle. So this will significantly affect the glucose level in the circulation, right? So a lot of glucose cannot be taken by skeletal muscle, particularly after meal and in a fat condition, so that causing the increased blood glucose level. And the other problem in the skeletal muscle is the mitochondrial dysfunction. So muscle is important tissue that oxidize fatty acids, right? So but for some unknown mechanisms, reasons that skeletal muscle actually have a decreased mitochondrial function. So muscle cannot be oxidize the fatty acids. So that will also lead to increased fatty acids in the circulation, right? They also contribute to. So the consequences of the insulin resistance in skeletal muscle is also causing increased blood glucose level because of decreased uptake, right, by skeletal muscle, and also decreased fatty acids oxidation and increased fatty acids in the circulation, right? So because of the mitochondrial dysfunction in skeletal muscle. And glycogen synthesis, yes.
Why in the muscle is GLUT4 expression the same, but in the adipose it's decreased?
Yeah, that's a great question. Usually, the different tissue, the regulatory mechanism is quite different. It's not always the same, right? So that's the adipose tissue again. The group 4 expression levels decrease, but not muscles remain the same levels, but the translocation decrease in both adipose tissue and the scalp muscle, right? All right. So liver. The liver is also one of the important metabolic tissues, like in terms of the regulation of blood glucose level. What liver does to regulation of blood glucose level? Do you guys still remember how liver contributed to glucose level maintains the homeostasis? Yes, glycogen breakdown release glucose, right? So basically increase glucose level, right, in the fasting condition. And what else, the pathways or mechanism that liver contributed to? Yes.
So the first here, insulin response. So our glucose is used to stimulate the insulin response that you produce.
So what liver does in response to insulin? Yeah. Glycogen, synthesizes glycogen, right, in the fat condition. So you see that actually multiple enzymes and pathways that can be regulated by insulin that contribute to the blood glucose level regulation, right? For example, glucokinase, which is enzyme that oxidize the metabolize glucose, right, in the first reaction in the glycolysis. And glucose 6 phosphatase and PEPCK, these are the two key enzymes, the gluconeogenesis, still remember, right? And glycogen synthesis is also the important enzyme that can be regulated by insulin. So in the insulin resistance, the liver, actually glucokinase activity is decreased, and these two key gluconeogenic enzymes actually increase, and glycogen synthesis is decreased. So what is consequences of all this change is have a decreased glycolysis. That means you have a decrease the uptake of glucose that then oxidizes, right? Because this is the first enzyme that being, they metabolize glucose, and the glycogen breakdown pathways is increased, and glycogen synthesis pathways decrease, and gluconeogenesis pathways increase. So particularly these two metabolic pathways, glycogen breakdowns increase and gluconeogenesis pathways also increase, and this will contribute to more glucose being produced from the liver and released into the circulation, right, in the insulin-resistant conditions. So again, in the type 2 diabetic patient, their liver makes more glucose and release into the circulation. So add even worse, right, to raise the blood glucose level. So three tissues together to make the more glucose being remain in the circulation, right? Muscle decrease uptake, adipose tissue decrease uptake, and liver increases output, right? To make more glucose and release circulation. And the other important issue in the liver is that because of the plasma fatty acids levels increase due to, can you guys tell me, due to two main reasons why plasma fatty acids levels increase in the type 2 diabetic patients. We just talked about it. Yeah, adipose tissue secrete more, right? Release more fatty acids because of high activities of lipolysis. And the other reason, low LPL, yes, and thinking about the tissue contributions. Right, mitochondrial dysfunction in skeletal muscle, right? So oxidize less fatty acids. So two things, comes together and make more fatty acids and circulating in the plasma, right? So increased plasma fatty acids is one of the important mechanisms for the liver synthesize triglyceride, right? Synthesis of triglyceride and causing fatty liver disease. So it's very common in the type 2 diabetes. The fatty liver is also developed in the, because of all these mechanisms, right? All right, so this is the last slide for this unit. I just wanted to talk about the sort called metabolic inflexibility. So if you compare the insulin sensitive, which usually in the lean, in health subjects, versus insulin resistance in the obesity or type 2 diabetic patients. In the fat condition, we have a lot of glucose, right, from the diet, and in that, let's say in the insulin sensitive condition, in the health condition, we can take up a lot of glucose, absorb a lot of glucose, right, and tissue is able to respond to increase the blood glucose, particularly pancreas, right, beta cell, and release insulin. And insulin is very important hormone in the fat condition, can stimulate or increase the glucose utilization, right, by, in multiple tissues. So in the fat condition, that our body is adapted to utilize more glucose for the energy, right, because of, a lot of tissues respond to insulin secretion, insulin levels increase. But in the insulin resistant obesity or diabetic patients, we also uptake a lot of glucose, right? Increase blood glucose levels, and you also be able to, at least in the at the early stage of a diabetic patient, their beta cells still respond to glucose and secrete insulin. But the problem is the insulin resistance, means the insulin action is decreased, right? It's insulin cannot does its function as efficient as in the lean condition, right? So a lot of tissue is not able to utilize glucose for the energy, particularly thinking about the muscle and adipose tissue, right? They cannot pick up or take up enough glucose from circulation, and so inside of cells, the glucose level actually is low, right? So you have sort of energy crisis, right, in the insulin responsive tissues like muscle and adipose tissue. So that, remember, we talked about before, right? That will increase the fat oxidation, fat utilization. But the problem is in the diabetic patient that mitochondrial function is also decreased, right? So they can actually utilize a lot of fatty acids as the energy. So it's energy level, the overall energy level in the cells actually lower, right, in the obesity type 2 diabetic, insulin resistant conditions. Okay, so I'll just finish this and then move on to the visualization in exercise. So in this session, what you guys need to know, and we're going to introduce a several concepts. So first of all, what is aerobic or anaerobic exercise, right? So aerobic exercise basically is a type of exercise that has a moderate intensity and undertaken a long duration. For example, marathon, this type of exercise usually considered the aerobic exercise. And anaerobic exercise is the high intensity and short-term exercise. For example, 100-meter sprint, this type of exercise, right, takes just 10 seconds. So this type short-term exercise usually is the anaerobic, right? And a second thing that we're going to talk about, the exercise intensity. Usually we use the so-called VO oxygen max to measure the exercise intensity, right? It measures how much oxygen be consumed by the body and to estimate, the exercise intensity. The more oxygen be used means that you oxidize more energy fuse and produce more ATPs that indicate that you have a higher intensity of the exercise, right? And then the respiratory quotient, RQ. RQ usually is the way to measure or estimate the fuel utilization in the skeletal muscle. What type of a fuel are used by skeletal muscle, like carbohydrate versus fat. How much fat, how much carbohydrate used in the skeletal muscle during exercise. So RQ is the measurement or estimate of fuel utilization. Another important thing is the sources of energy fuels that our body utilizes for exercise. And so during exercise, the muscle usually use the most two important energy fuels, fat and carbohydrate and fat, right? And you need to know where are these carbohydrates or fatty acids comes from during the exercise. And the next is the fuel utilization in aerobic and anaerobic metabolism. So aerobic and anaerobic metabolism utilize different type of energy fuels, right? You keep in mind this is and also involve a different type of muscle fibers. And post-exercise recovery period, when finish the game or an exercise, and our body need to rebuild the glycogen, and in this particular time period, the body use a specific type of energy fuels in order to rebuild glycogen, muscle glycogen. And also you need to know the muscle adaptation response to training, right? So how muscle responds to training or changing, some characteristics and fuel utilization. And lastly, the carbohydrate loading. This is kind of an intervention to increase the muscle glycogen, right? Muscle glycogen is very important for an exercise performance. So we wanted to have a higher muscle glycogen store before competition and something like this. So, all right. So before we talk about the muscle exercise, the metabolism exercise, and I wanted to talk about the muscle fibers. So this is very important. You guys wanted to remember, and this, I think, this is very important table, right? So why we need to talk about muscle fibers? So different type of muscle fibers that involve different type of exercise, and different type of fibers that does different metabolism. Aerobic versus anaerobic metabolism. All right. So basically, our body has three major muscle fibers. Type 1, red fibers. type 2A red fibers and the type 2X white fiber, right? 3 different fibers. And I can tell you the tricky, right, to tip, how to memorize this. So type 1 and type 2X is very different, very different fibers, right? And type 1 basically is oxidative, and type 2X is glycosidic, the low oxidative. So I already highlighted here the red row, all right? So once you remember this, it's very easy to remember the other characteristics, right? So mitochondrial content, mitochondrial density. I mentioned the type of 1 is the oxidative fibers, right? So that means they have higher mitochondrial content. And type 2X has a lower mitochondrial content, so have a lower oxidative capacity, right? And type 2A is sort of the intermediate, right, in between. So just try to remember type 1 and type 2X, and type 2A is intermediate. So the type 1 is higher mitochondrial content, and type 2X is a lower mitochondrial content, right? So type 1 has the higher oxidative capacity, and type 2X is lower oxidative capacity, right? And in terms of glycolytic capacity, because of type 1 has a lot of mitochondria usually just do the oxidative metabolism, right? Complete oxidized energies fuse. So the glycolytic capacity is lower. But type 2X, because of lower mitochondria, so they heavily rely on the glycolysis, right, to oxidize glucose. So the glycolytic capacity is high in type 2X. And then the glycogen content. So what do you think glycogen content in type 2 and type 1 and type 2X? Which muscle fibers that requires more, need more glycogen? Yes. Yeah, type 2X, right? Because the more higher glycolytic capacity, so they requires or need more glycogen for energy. So more glycogen is stored in the type 2X fibers as compared to lower or less glycogen stored in the type 1 fibers. And how about the triglyceride content? Which type should have a higher triglyceride content? Type 1, right? Type 1 is a higher oxidative capacity. They're able to oxidize fatty acids, right? So it should have a higher triglyceride content. And then creatine phosphate content. Creatine is the important energy fuse for anaerobic metabolism, right? We're going to talk about later. But here so it also makes sense, right? The type 2X should have a higher creatine phosphate content. And then you look at the ATP production. And so in the type 1, because of high mitochondrial content, it does a more aerobic metabolism to make ATPs, right? And versus anaerobic system of metabolism in type 2X to make ATPs. And also activities for different type of exercise. For type 1, because of it's anaerobic, right? And it's aerobic fibers, so it's more suitable for the long distance running like a marathon, right? Type 1. And the type 2X is more suitable for short term, the anaerobic metabolism, like sprinting, right? And also the fatigue, resistant to fatigue. So which fibers? Fatigue is actually related to the lactate acid production. So higher lactic acid is the cause of a fatigue, right? So probably I think it was also very easy to understand, right? Because the type 2X is more glycolic, so because lower mitochondrial content, so glucose is mostly metabolized through the glycolytic pathway, right? And the partial glycolysis pathway. So produce a lot of lactate in type 2X. So type 2X is lower resistant to, it's very easy to get fatigue, right? And type 1 is more, oxidative and have less lactate production, so it's resistant to fatigue. And then the percentage, usually in our body, 50% of fibers are type 1, and 40% of fibers are type 2A, and only 10% of fibers are type 2X. Right. Any questions about this table? I think it's very important. Try to remember it's two different types, how they does the the energy metabolism and how they involve in different type of exercise. So I just give you a little bit more information, but actually basically to review again the type of different three different type fibers. The type 1 is the slow twitch fibers, right? It's a higher because oxidative capacity, because higher mitochondrial content, and mostly does the aerobic metabolism. Particularly, it's able to oxidize fatty acids, right? So does fat oxidation, and it's suited to perform endurance exercise, long-term distance running, for example. So how is the glucose metabolized in type 2 fibers? How is glucose metabolized? Partial or complete? Yes, complete. So type 1 fibers, in the type 1 fiber, glucose can be complete oxidized, right, to CO2 water, and it produces ATPs because of higher mitochondrial content. They are able to do this, so have less lactate produced, right, in the type 1 fibers. And type 2A is sort of intermediate. It's fast twitch, and they modulate oxidative capacity, and higher glycolytic capacity. So type 2A fibers are able to do both aerobic and anaerobic metabolism, right, and perform like middle distance running or swimming. This is the type of fibers. And type 2X is basically a lower mitochondria, lower oxidative capacity. Yes, questions?
How are the terms oxidative and glycolytic different? Because usually when we talk about glycolysis, it's also glucose oxidation.
Right. So oxidative mostly refers to like complete oxidation, right? Requires mitochondria and oxygen. And glycolic here, particularly, I think is talking about just the partial oxidation. You use anaerobic metabolism of glucose, right? So 2X, type of 2X is the very high glycolic capacity because of a lower mitochondrial content. So that's anaerobic metabolism, right? So how is glucose metabolized in type 2 fibers? Partial glycolysis, right? Oxidation. So glycolysis and produce high levels of lactate, right? So again, the type 2 fibers are the major contributors to lactate production during the exercise because of the anaerobic metabolic characteristics. So because of this, the type 2 fibers, it's very easy to become fatigued, right? Because lactate production. So this type of fibers is usually specialized to perform the sprinting exercise, very short-term exercise. All right. So so in the long-term exercise, at the 60-75% of VOX2 max, this is kind of a exercise intensity. We're going to talk about a couple slides later, right? So means that in the these levels of intensity and the long-term exercise, the type 1 and the type 2A fibers are first recruited during the early stage of exercise, right? Again, in this long-term moderate intensity exercise, the type 1 and the type 2A fibers are first recruited at the beginning of the exercise. And at exercise prolongs, the type 2X fibers then are recruited and activated to maintain the levels of intensity, right? So remember, the type 2 fibers are the major contributor to the lactate production, right? So that's why at the later stage of exercise, because of the type 2 fibers are recruited and oxidize glucose and produce a lot of lactate, so that you feel kind of fatigued, right, in the later stage of exercise. Okay, now let's talk about the different type of exercise, aerobic versus anaerobic exercise. So aerobic exercise, again, is a moderate intensity and taking long-term duration. The good example is the marathon. Aerobic exercise requires oxygen, right? And during the energy producing process, means that involved mitochondria, requires energy and involves the mitochondria to complete oxidized energies to produce a lot of ATPs. And aerobic exercise, anaerobic exercise again is the short-term, high energy required exercise, like 100 meter sprinting, right? It's very short term. And why it's anaerobic? For this short-term exercise, why is anaerobic? We know during exercise, particularly this high intensity exercise requires a lot of energy, right? A lot of ATPs, and muscle need to oxidize. And also this very short time period, 10 seconds, we need make a lot of ATPs. But because of time is too short, only 10 seconds. If we do aerobic exercise, we'll need oxygen, right? And within this 10 seconds, it's not possible to get oxygen, that quick to deliver to the skeletal muscle, right? For oxidation, for ATP production. So this is the reason that the very short-term exercise we usually do the anaerobic exercise. That. So this is the reason the oxygen cannot be transported quickly enough to the skeletal muscle to meet that. The large amount of needed of oxygen for ATP production, right? Okay, so how to define the exercise intensity? This is also something we need to know. So exercise intensity usually is determined by the muscle contraction cycles per unit of time, right? So if you contraction cycles, you have more, the higher exercise, the higher exercise intensity, the more contraction cycles are needed for per unit of time, right? And that means more ATPs are needed, right, to be synthesized per unit of time, and also more fuels that are needed to be oxidized. Right? So the intensity of exercise usually is related to the oxygen consumption, right? The oxygen, the oxidative activities requires the higher levels of oxidative metabolism and requires, more oxygens, right? Is higher if exercise intensity is higher. Now that makes sense, right? And also keep in mind that the rate of active synthesis, ATP synthesis, and the fuel utilization in muscle are increased during the exercise. Right? So this is how we measure the exercise intensity. And in the last study, I just mentioned that exercise intensity is related to the oxygen consumption, right? The higher the exercise intensity, and then you need more oxygen to make more ATPs, right? So, so in order to measure the exercise intensity, we usually use the oxygen consumption rate to determine the exercise intensity, right? So VO2 max is the person maximum aerobic capacity defined as 100%. So this VO2 max in different individuals can be different. And for example, the chained versus unchained, the chained individuals may have a higher VO2 max. Right? That means the maximum oxidative capacity or aerobic capacity that a person can reach. Right? And we measure oxygen intensity by measuring the oxygen consumption. The volume of the maximum volume of oxygen can be used by the body during exercise by measuring the utilization or oxygen consumption to indicate how much the oxidative capacity, oxidative activity in the body during the exercise. Does that make sense? Right. So here I just wanted you to remember these three numbers, right? Indicate the different levels of exercise intensity. For example, for the low intensity exercises, for example, faster walk, and this low intensity exercise usually you only use 25% of your maximum oxidative capacity, right? And the moderate intensity of exercise, like fast jog, utilize 60% of your maximum oxygen capacity, right? And high intensity, like marathon, and you usually use this 80% of the maximum oxygen capacity, right? So remember, three different percentage indicate the different levels of intensity exercise. 25% for low intensity, 60% moderate intensity, and 80% for high intensity, right? Okay, now let's take about a 10 minutes break. Okay, let's move on. Um, so the exercise intensity, right? You know the definition, how to measure the exercise intensity. Basically, to measure the maximum volume oxygen consumed by the body during the exercise to indicate, the oxidative capacity, and also the different levels, right? The low 25% and moderate intensity, you see 60%, the high intensity, you see 80% of the maximum oxygen consumption or capacity. And oxygen utilization is actually linear related to energy expenditure. Does that make sense? Right? Your oxygen is required for oxidative metabolism, right? To oxidize fatty acids and to, and we remember we talked about before that it's an important way to get rid of the fat is to oxidize fat, right? So if this process requires oxygen, so if we consume more oxygen, able to consume more oxygen, that means we oxidize more fatty acids and increase energy expenditure. And greater consumption, right? Really greater, intensity of exercise, right? It's also related to the intensity of exercise ATP production. And two important things that you probably wanted to know that training can increase oxygen consumption. That means the VO2 max can be increased by the training, so even can increase by 15 to 20% of the VO2 maximum. Again, the VO2 maximum is different in different individuals, right? Training can increase VO2 max, increase oxygen consumption, the oxidative capacity, which is important for the performance, right? Now let's talk about the fuel utilization in skeletal muscle during the resting state. You're not exercise, right? The resting state. This we already mentioned before, right? When we talk about fuel utilization in the fat and fasting condition. So in the fat conditions, the muscle basically utilize a mixture of the carbohydrate and fatty acids. And RQ will be like around the 0.92. And in the fat condition, we're going to talk about later, what does the RQ 0.92 means, right? When we get there. So in the fat condition, muscle utilize more glucose, and glucose is a major energy fuel for the skeletal muscle in the fat condition. I'm talking about a resting condition, right? Resting state. And during the fasting, muscle utilize more fatty acids and even ketone bodies, right? The very late, the very long-term starvation. And two important points that I want to make, and here is one is the most of energy fuels is a primary source of energy fuel for muscle use during resting condition is the blood-borne fuels from the circulating. The blood-borne fuels are the primary sources of energy fuels for the skeletal muscle during the resting conditions. Means that in the fat condition, the glucose basically is from the diet, right? The circulating glucose from the diet. So in the fasting condition, the blood glucose basically from the glycogen breakdown from the liver or gluconeogenesis from the liver and kidney, right? So the circulating or blood-borne energy fuels or circulating energy fuels are the major source of energy for the skeletal muscle during the resting condition. And intracellular fuels are not that important, right, for the skeletal muscle during resting condition. Remember, the skeletal muscle actually store a lot of glycogen, right? So muscle glycogen and skeletal muscle also store some amount of a triglyceride. So the intramuscular triglyceride and muscle glycogen are not important energy fuels for the skeletal muscle during the resting condition, but they are important energy fuels during the exercise with skeletal muscle, right? So it's different energy utilization and sources of energy between resting and exercise. Okay, now let's talk about the fuel utilization skeletal muscle during exercise. In general, in addition to carbohydrate, fatty acids, the muscle can also use the creatine phosphate, right? Creatine phosphate is important energy fuel for anaerobic metabolism. Remember, type 2X fibers is anaerobic fibers, right? That's higher content of creatine phosphate. So creatine phosphate is important energy fuel for anaerobic metabolism in type 2X fibers. And in terms of the sources of carbohydrate and fatty acids, and the carbohydrate can be from the diet, circulating blood glucose basically from the diet, and also from glycogen, liver glycogen breakdown, right? And muscle glycogen is also very important. The carbohydrate sources of energy during the exercise. And the fatty acids can be from the diet, in the circulation, right? And triglyceride as also important source of fatty acids. And remember, muscle also contains lipoprotein lipase, right? Can hydrolyze triglyceride and release fatty acids. And this muscle LPL can be increased or activated during the exercise. Remember, fasting or exercise, both fasting and exercise can stimulate LPS activities in skeletal muscle. And the other sources of fatty acids or fat is intramuscular triglyceride, right? The muscle is also store some levels of triglyceride, and which is important sources of energy during exercise, right, for skeletal muscle. And energy expenditure is increased here. Just some kind of a point that you probably wanted to know, that energy expenditures increase in the skeletal muscle, and because of the availability of carbohydrate fatty acids increase. We're going to talk about later why the carbohydrate and fatty acids can be released or increase the availability during the exercise because of hormone levels change, right? And the ability of the muscle to oxidize both carbohydrate fatty acids also increase, and this two processes also being, and again, it's regulated by the hormone levels, right, during the exercise. So this all working together to increase the energy metabolism, to increase ATP production during the exercise. And energy cost, right? Muscle contraction requires a lot of ATPs, right? A lot of energies. So the shortening of movement, that the need to oxidize or hydrolyze the ATPs, right, to release energy. And the three important enzymes that hydrolyze ATPs and release energies, myofibril ATPase, right? And sodium, potassium ATPase, and calcium ATPase, right? 3 ATPase in the muscle fibers that can hydrolyze the ATPs and release energy for muscle contraction. Another important thing is that the body utilizes actually only about half of skeletal muscle for running marathon. When we do exercise, not all the muscle that involved, the exercise, only half of muscle that involved even for the running a marathon, only half of muscle that are involved. And most of the ATPs that are required for marathon is produced from the aerobic metabolism, right? The marathon is a long-term exercise, usually is type of aerobic exercise, right? So ATP is produced for running marathons, basically is from aerobic oxidation or metabolism of carbohydrate and fatty acids. So which type of fibers you think will mostly involve the marathon? Thinking about, yes, aerobic fibers, type 1, right? And type 2A. And most of the ATPs for a 100 sprint, which is a short-term and anaerobic metabolism, right, is generated from creating phosphate and glycogen, right? The glycogen within the skeletal muscle. So creating phosphate and glycogen are the major sources of energy for anaerobic metabolism, for short-term running, right? And here just give you some idea how the process of ATP production, right? ATP generated, usually generated from oxidation of glucose and fatty acids, and 3 enzymes and ATPase hydrolyze ATP to ADP and release energy, right? And energy is required for muscle fiber shortening movement and depolarization of the muscle cell membrane in response to nerve signals, right? And calcium also need to be released from sarcoplasmic reticulum into the cytosol, right, in order to make contraction or movement of muscle fibers. So energy needed for all these activities during the exercise, right, the skeletal muscle. Now let's move on to the sources of the carbohydrate and fat for oxidation in skeletal muscle during exercise. And again, the different type of exercise utilize the energy from different sources, right? Let's first talk about the aerobic exercise. Aerobic exercise, carbohydrate and fatty acids are the major energy source, right? Again, the fatty acids only being able to use during aerobic exercise, right? Only be able to use by type 1 and type 2 fibers because they are aerobic fibers. They have a higher mitochondrial content. So glucose can be from blood circulation and can also be from the muscle glycogen breakdown. And blood glucose usually from the dietary glucose and liver glycogen breakdown released into the circulation, right? The two main sources of glucose for the blood glucose, right? From the two main sources, dietary glucose and the glycogen breakdown from the liver. And fatty acids, it also can be from circulation, which originally from dietary lipids, and lipolysis of fatty acids, right, release triglycerides, sorry, lipolysis of triglyceride and release fatty acids into circulation. And also some triglyceride in the lipoproteins, particularly VLDL, remember. And intramuscular triglyceride is also sources of fatty acids used by skeletal muscle. So again, for aerobic metabolism, the muscle utilizes both glucose and fatty acids as energy fuels. Right? Glucose basically from the circulation, diet, and liver glycogen breakdown, and also intramuscular the glycogen breakdown. And fatty acids is also from circulating dietary lipids, and also important sources of the adipose tissue, right, from the lipolysis. And intramuscular triglyceride is also the sources of fatty acids in the aerobic exercise. Here the slide show us just give us a little bit more, better pictures of the sources of glucose or carbohydrate for the exercise for skeletal muscle. Again, the dietary carbohydrate, right, contribute glucose to circulation and pick up by muscle, right, utilized in the muscle. So this is one source of glucose. And the second source of glucose is from the glycogen, liver glycogen breakdown, and also released into circulation and go to the muscle for oxidation. And the third source of carbohydrate is the glycogen, right, muscle glycogen breakdown. So if you compare the how much glucose being contributed from 3 different sources, you can see actually skeletal muscle, the glycogen, muscle glycogen is a major contributor, right, to the glucose. See, compare 300 to 800 gram in glycogen stored in the skeletal muscle versus only 60 gram from the diet, and liver only stores 70 to 80 gram of glycogen, right? So again, the muscle glycogen is the major sources of glucose that are utilized by the muscle during exercise. So muscle glycogen is very important for the performance of the the muscle fibers and exercise. So a couple of questions here. Where does glucose use in skeletal muscle come from during aerobic exercise? We already talked about it, right? 3 major sources, muscle glycogen, liver glycogen, and dietary carbohydrate. But muscle glycogen is a major source of carbohydrate, right? And the second question is, how is glucose metabolized during aerobic exercise in the skeletal muscle? It's complete oxidized, right? See, the glucose to aerobic metabolism, complete oxidized and produce ATPs. And here's 2 things that you might want to know, that the type 1 and type 2 fibers usually does the aerobic metabolism, right? So glucose usually is complete oxidized in type 1 and type 2A fibers, right, and produce ATPs. And type 2X fiber, because it's anaerobic fibers, right, and that's anaerobic metabolism. So glucose is partially oxidized and produce lactate in the type 2 fibers. So again, the type 2 fibers are the major contributors to the lactate production and the fatigue, right? It's related to fatigue. Any questions? Now let's talk about fat oxidation, fat availability during the exercise. Remember the exercise, during exercise the sympathetic nervous system being stimulated, right, and release a lot of catecholamines, particularly norepinephrine, and these catecholamine levels increase, and the big drivers of the lipolysis in the adipose tissue, right? So catecholamine can stimulate the hydrolysis of triglyceride or lipolysis and release fatty acids, right? So increase a lot of fatty acids being released from adipose tissue during the exercise because of the increased catecholamine levels, right? And liver picks up, although the loss of a majority of fatty acids that released from adipose tissue can be uptaken by muscle and utilized in the muscle, but still have some fatty acids kind of leak, right? They cannot be picked up by the liver and by adipose tissue, the muscle, and then will be picked up by the liver, and in the liver this fatty acid being synthesized to triglyceride again and packed to VLDL and then released again to the circulation and picked up by the skeletal muscle, right? Remember this LPL enzymes that also increase and release in the skeletal muscle during exercise, and this LPS does the function to break down triglyceride and allow fatty acids being released and picked up by skeletal muscle, right? And lastly, the triglyceride also stored in the skeletal muscle, right? It can be breakdown, and this. Do you guys remember what enzyme that break down the triglyceride inside of cells? No? HSL, yes, thank you. HSL, right? So hormone-sensitive lipase in skeletal muscle can also be activated during exercise, so and hydrolyze triglyceride inside of skeletal muscle and release fatty acids. And again, this is the aerobic metabolism, right? So all the fatty acids can be completely oxidized, go to the beta oxidation in mitochondria, and produce ATPs. So this, the fatty acids utilization requires mitochondria, right? So only this process, the fatty acid utilization occurs in the two muscle fibers, type 1 and type 2A fibers, right? A similar question that I hope you guys will be able to address, like where do fatty acids used in skeletal muscle come from during aerobic exercise, right? The three sources, fatty acids, the adipose tissue lipolysis, intramuscular triglyceride lipolysis, right? And the liver release the VLDL, the triglyceride. And I wanted to point out that the adipose tissue is a major source of fatty acids during the exercise, right? And second question, how are fatty acids metabolized during the aerobic exercise, or in which type of fibers that fatty acids can be metabolized? Type 1 and type 2A, right? And complete oxidized through the beta oxidation in mitochondria. And so mitochondria and oxygen are required for fatty acids oxidation in muscle fibers. So more information about aerobic metabolism. The aerobic metabolism requires oxygen and mitochondria, right? So during the aerobic exercise, the oxygen uptake is increased, right? We need to produce more ATPs, so you need more oxygen to oxidize fatty acids, right? Or glucose in the mitochondria in the aerobic fibers. So for aerobic metabolism to occur, there must be increase, right? Because we need more oxygen, right, to oxidize the energy fuels. So oxygen delivered to the tissue, particularly to the muscle, is need to be increased. So how we're going to increase oxygen delivery? So several kind of physiological adaptations, right, occur to increase oxygen the uptake. Right? First of all, increase the heart rate, right? Increase the heart rate and volume, and to increase the oxygen delivery, and then the breathing rate is also increased, right? Heart rate and breathing rate increase, it's increase the uptake of oxygen, and then the blood flow is also increased to the muscle, so it can increase the delivery of oxygen. So this is the physiological adaptation to exercise. The purpose of this is to increase the oxygen delivery and uptake and delivery to the skeletal muscle, because skeletal muscle need oxygen to oxidize fatty acid glucose for ATP production, right? So changes in the fuel metabolism means that during the whole time period of exercise, the fuel utilization is not always consistent. So for example, from low to moderate to high intensity exercise, as the exercise intensity increase, the carbohydrate utilization is increased, right? But the fat utilization is different. So from low to moderate intensive exercise, the fat utilization is increased, but when your intensity increases more, for example, from moderate to high intensity of exercise, the fat utilization actually decrease. So we need to know this because this kind of related to the exercise performance, right? Again, for the carbohydrate utilization is continuous increase from low to moderate to high intensity exercise, the whole period of exercise, right? The carbohydrate utilization continues increase. So mean that our muscle will be able to utilize more and more carbohydrate. The ability to utilization of carbohydrate is increased. But for the fat utilization, from low to moderate, fat utilization is increased, but start from moderate to high intensity exercise time period, the fat utilization is decreased. So that means during the moderate to high intensity exercises time period, we need to rely on more carbohydrate, right? So carbohydrate, the glycogen store is very important. If you have a higher glycogen store, then you be able to perform well during this, the later moderate to high intensity period, right? Because of your fat utilization decrease. So even you have fatty acid available, because you cannot utilize fatty acids, so you have to utilize carbohydrate in order to make similar levels of ATP production. Um, let's see. I think we have informal writing today, right? One thing that I wanted to ask you guys, have you guys received the email regarding like a teaching evaluation? You guys did? Okay. And could you guys do me a favor and to please to, make your comments and take a couple minutes, right? I enjoyed this class very much, and you guys did very well, and you guys worked very hard. So I really appreciate. And for informal writing today. So since the fibers is very important, right? So I just want a guy to, emphasize this concept. So try to describe the differences in metabolic characteristics of the type 1 and type 2 muscle fibers. And try to focusing on the mitochondria, make a comparison, right? And focusing on the mitochondrial content, oxidative capacity, glycolytic capacity, aerobic versus anaerobic system used for ATP generation, and also what type of exercise activity used for different type of fibers. Right? Question? Yes. Yeah. That will be fine. Yeah. Make a table. It should be most efficient, right?